Right. 1968, the height of the space race. The United States and the Soviet Union are in a fierce competition to conquer space, each striving to outdo the other in technological innovation. But amidst this high-stakes game, one groundbreaking project slips beneath the radar, its potential impact on space travel yet to be realized. This is the story of NERVA, NASA's covert nuclear thermal rocket program. At the time, the United States had already made significant strides in developing chemical propulsion technology for their spacecraft. However, these engines were limited in their ability to efficiently propel heavy payloads over long distances, a major hurdle in realizing President Kennedy's dream of landing a man on the moon and returning him safely to Earth. Enter NERVA, an ambitious initiative that sought to harness nuclear energy to create a powerful new type of rocket engine. The concept was simple yet revolutionary: use nuclear fission to heat hydrogen gas, which would then be expelled through a nozzle to generate thrust. This nuclear thermal rocket promised twice the efficiency of conventional engines and could potentially cut travel time to Mars by half. So why haven't you heard about NERVA before? The answer lies in a complex web of political maneuvering, budget constraints, and public perception. Despite promising results from numerous ground tests, the project faced mounting opposition from anti-nuclear activists who feared the potential dangers of launching nuclear-powered spacecraft. Additionally, the success of NTR technology threatened the vested interests of powerful aerospace contractors who had heavily invested in chemical propulsion systems. As the public's attention shifted towards other priorities, such as the Vietnam War and civil rights movement, funding for NERVA began to dwindle. In 1973, citing budgetary concerns, NASA officially terminated the project just 1 year shy of a planned space test that would have demonstrated NTR technology's viability for deep space missions. But the story doesn't end there. Decades later, interest in nuclear propulsion has resurfaced as humanity looks to extend its reach into the cosmos. Organizations like NASA and private companies such as SpaceX are once again exploring NTRs as a means to enable manned missions to Mars and beyond. The legacy of NERVA serves as both a cautionary tale and a beacon of hope for future generations. It reminds us that groundbreaking ideas can be derailed by short-sighted politics and fear, but also inspires us to continue pushing the boundaries of science and technology in our quest to explore the universe. As we delve deeper into the mysteries surrounding NERVA, join us on this investigative journey to uncover the untold story of NASA's secret nuclear thermal rocket program and its potential impact on humanity's future in space. In the early days of space exploration, during the height of the Cold War, the United States and the Soviet Union were locked in a fierce competition to assert their dominance. This era, known as the space race, pushed both nations to develop cutting-edge technologies and explore the cosmos' unknown realms. One such technology, NASA's nuclear thermal rocket, promised to revolutionize space travel, but was abruptly cancelled amidst controversy and secrecy. The NTR, or NERVA, was a joint project between NASA and the Atomic Energy Commission. The program aimed to create a nuclear-powered engine capable of propelling spacecraft to Mars and beyond. NTRs were significantly more efficient than conventional chemical rockets, requiring less fuel and allowing for faster, cheaper missions. The key players in this story include Dr. Hans Bethe, a Nobel laureate in physics who advised the AEC on NERVA's development, Dr. Kurt Debus, NASA's first Kennedy Space Center director, and Wernher von Braun, the renowned German-American rocket scientist who led the development of the Saturn V launch vehicle. The NERVA project began in 1955 under the Eisenhower administration, with the first successful test firing taking place in 1961 during the Kennedy presidency. Despite this promising start, the program faced numerous challenges, including budget cuts, safety concerns, and changing political priorities. By the late 60s, NERVA had made significant strides, conducting several full-scale engine tests with impressive results. However, in 1972, amidst growing public concern over nuclear power and a shift in focus towards the Space Shuttle program, NASA officially cancelled NERVA. This decision raised questions about the true reasons behind the project's termination. Some speculate that it was due to budget constraints, while others suggest that political pressure from anti-nuclear advocates played a role. The cancellation of NERVA had far-reaching consequences for the future of space exploration. With the demise of NTR technology, chemical rockets remained the primary means of propulsion, limiting the distance and duration of missions. This meant that Mars, once considered a viable target for manned exploration in the 60s, remained out of reach for several more decades. As we continue to explore the mysteries surrounding NERVA, it's essential to consider the broader context of the Cold War space race and the political pressures that influenced scientific progress. The story of NASA's secret nuclear thermal rocket program serves as a reminder that scientific advancements can be derailed by short-sighted politics and fear, but also inspires us to continue pushing the boundaries of science and technology in our quest to explore the universe. In the annals of space exploration, few subjects remain as shrouded in mystery as NASA's cancelled nuclear thermal rocket program. To truly appreciate the potential of this technology and understand why it was set aside, we must first demystify the science behind nuclear thermal rockets and their proposed role in deep space exploration. Nuclear thermal propulsion is a method of spacecraft propulsion that uses a nuclear reactor to heat liquid hydrogen fuel, which then expels through a nozzle to generate thrust. This process is far more efficient than traditional chemical rockets, which rely on exothermic reactions between fuels and oxidizers. In fact, NTP can theoretically deliver twice the efficiency, making it an ideal candidate for long-duration missions to Mars and beyond. The concept of nuclear thermal propulsion is not new. It has been studied since the 1950s by organizations such as NASA and the Atomic Energy Commission. One notable design from this era was the nuclear engine for rocket vehicle application, which underwent ground testing between 1959 and 1972. NERVA's successor, the Space Nuclear Thermal Propulsion Project, aimed to develop a flight-capable nuclear thermal rocket by the late 1980s. At the heart of an NTP engine lies a nuclear reactor, where uranium or plutonium fuel rods heat liquid hydrogen passing through the core. The heated hydrogen is then expanded through a nozzle to produce thrust. This design allows for greater specific impulse, a measure of how efficiently a rocket uses propellant, compared to chemical engines. In other words, NTP can achieve the same performance using less fuel, making it an attractive option for deep space missions with limited payload capacity. Despite its potential benefits, NASA's nuclear thermal rocket program faced numerous challenges throughout its development. These ranged from technical hurdles in reactor design and safety concerns to public perception and political pressures. The latter was particularly evident during the Cold War era, when military and strategic considerations often overshadowed scientific progress. In 1968, the SNTP project received a significant setback when an AEC-funded reactor explosion at the National Reactor Testing Station in Idaho killed 3 researchers. This accident, along with growing anti-nuclear sentiment, contributed to the public's apprehension towards nuclear-powered spacecraft. By the late 1970s, NASA had shifted its focus away from NTP in favor of chemical and electric propulsion technologies. While these alternatives offered safer and more politically palatable options, they fell short of NTP's performance capabilities. As a result, deep space missions have been relegated to slower travel times and increased logistical challenges. The question remains, why did NASA abandon such a promising technology? The answer lies in the complex interplay between scientific advancements, politics, and public perception. The story of NASA's nuclear thermal rocket program serves as both a cautionary tale and an inspiration to continue pushing the boundaries of science and technology in our quest to explore the universe. And so, despite its technical triumphs, NERVA's future began to dim. The project had already consumed over $1 billion, making it one of the most expensive undertakings in NASA's history at that time. Yet, it wasn't just about money, there were political and public perception factors at play too. The late 1960s and early 1970s saw a significant shift in American priorities. The Apollo missions had achieved their goal of landing men on the moon, but public enthusiasm for space exploration waned as budget constraints tightened. Moreover, the growing anti-nuclear movement in America added to the pressure on NASA to abandon its nuclear projects. In 1972, President Richard Nixon announced a significant restructuring of the U.S. space program. The emphasis shifted from manned missions to scientific satellites and unmanned exploration. This shift signaled trouble for NERVA. Without strong political backing or public support, funding for the project dried up. In 1973, NASA officially canceled the NERVA program. But did it have to be this way? Some argue that the cancellation of NERVA was premature and unjustified. Dr. Charles Lafange, former director of the Lewis Research Center, testified before Congress in 1971 that the nuclear rocket is the only power source capable of taking us to Mars within any foreseeable time. Yet, his warning went unheeded. Even today, many questions surrounding NERVA's cancellation remain unanswered. For instance, why did NASA not explore alternative funding sources when it became clear that Congress was unwilling to continue financing the project? And why were no private companies interested in taking over or investing in the technology? One possible explanation lies in the broader context of Cold War politics. By the early 1970s, the US had already won the race to the moon and was looking for ways to reduce military spending. In this climate, a costly and controversial project like NERVA may have seemed like an easy target for budget cuts. Moreover, the growing anti-nuclear sentiment in America might have made it difficult for NASA to justify continuing with a nuclear-powered spacecraft. As public opposition to nuclear technology grew, so did the calls for alternative energy sources. In this context, investing in a controversial technology like NERVA might have seemed risky and ill-advised. Yet, the cancellation of NERVA marked a turning point in America's space program. It represented the end of an era defined by bold ambitions and technological daring. Since then, no manned mission has ventured further than the moon, and our dreams of exploring the cosmos remain largely unfulfilled. As we look back on NERVA today, we are left with a sense of what might have been. We see a promising technology suppressed by political considerations and public perception, and we are reminded that the story of scientific progress is often as much about politics and people as it is about ideas and innovations. In the end, the cancellation of NERVA serves as both a cautionary tale and a call to action. It reminds us that the pursuit of knowledge requires courage, perseverance, and a willingness to challenge conventional wisdom, and it inspires us to continue pushing the boundaries of science and technology in our quest to explore the universe. Delving deeper into our exploration of NASA's cancelled nuclear thermal rocket program, we find ourselves at the heart of a genuine mystery. The project, known as NERVA, was abruptly halted in 1973, leaving behind not only a pioneer in technology, but also a trail of unanswered questions and classified documents that remain shrouded in secrecy to this day. The decision to terminate NERVA came as a shock to the scientific community, particularly when considering its potential to revolutionize space travel. With its ability to reach speeds 5 to 10 times faster than conventional chemical rockets, nuclear thermal propulsion could have drastically reduced trip times to Mars and beyond, making mankind's dream of interplanetary exploration a tangible reality. So why was such a promising project abandoned? The official explanation points to budget cuts and changing priorities within NASA. However, numerous indicators suggest there may be more to the story than meets the eye. One intriguing piece of evidence is the existence of STG-3, a top-secret research facility at the heart of the NERVA program. Located in Las Vegas, this clandestine lab was home to some of the most innovative work on nuclear propulsion systems. Yet, despite its significance, STG-3 remains largely absent from official histories and public records. Another curious detail surrounds the fate of key NERVA personnel. Many of the program's leading scientists and engineers vanished from the public eye shortly after the project's cancellation. Some were reassigned to other divisions within NASA, while others disappeared entirely, their names and contributions expunged from official records. The most intriguing clue, however, lies in a series of classified documents that have recently come to light. These files reveal details of several experimental tests conducted during the final years of NERVA, tests that pushed the boundaries of nuclear propulsion further than ever before. Yet, these breakthroughs were never publicly acknowledged or integrated into the mainstream scientific narrative. One such experiment, codenamed Project Pele, involved the successful testing of a small-scale nuclear thermal rocket in 1972. The success of this test marked a significant milestone in nuclear propulsion technology, yet it remains largely unknown outside of classified circles. The question then arises, why would NASA suppress the achievements of its own visionary team? Some argue that the answers lie not in scientific shortcomings but in geopolitical considerations. With the Cold War raging and tensions between superpowers at an all-time high, the prospect of a rival nation harnessing such advanced technology may have been too great a risk to bear. In conclusion, while we may never know the full story behind the cancellation of NERVA, one thing remains clear: the tale serves as a potent reminder of the complex interplay between politics, people, and science. As we continue to push the boundaries of knowledge and exploration, let us not forget the lessons of the past, nor the sacrifices made by those who dared to challenge conventional wisdom in pursuit of a better future. The cancellation of NERVA didn't just silence a powerful engine, it also marked the end of an era in space exploration. Apollo had achieved its lunar mission, and public interest waned as budgets tightened. Yet, the allure of nuclear propulsion persisted. In the aftermath of NERVA's demise, pieces of the program found their way into other projects. For instance, some components were used in the US Navy's submarine reactors. However, much of the technological breakthrough and data amassed during those 2 decades remain classified, locked away in secure government vaults. Today, nearly half a century since NERVA's untimely demise, we stand on the brink of another nuclear revolution in space travel. New designs like the NASA-funded Nuclear Electric Propulsion System aim to cut travel time to Mars from months to weeks. These systems promise not only faster trips but also reduced radiation exposure for astronauts and less dependency on planetary gravity assists. Moreover, private companies are joining the race. Blue Origin's New Glenn rocket, slated for launch in 2021, will use liquid hydrogen and LOX engines, technology directly linked to NERVA. SpaceX's Raptor engine, powering their Starship spacecraft, is also a Methalox-staged combustion engine, sharing design philosophies with nuclear thermal rockets. Yet, despite these advancements, no country has fully reignited a national effort to develop a nuclear thermal rocket since NERVA. The question remains, why? When we are closer than ever to realizing the dream of reliable, efficient nuclear propulsion, does it seem like we're still stuck in neutral? Perhaps the answer lies within the shadows of history. The specter of Cold War competition that birthed NERVA has morphed into something more complex and less defined. International treaties, environmental concerns, and public perception all play their parts in shaping this new landscape. Or maybe, just maybe, there are still secrets hidden deep within the classified records of agencies long past their heyday. Secrets that could change everything we know about why we haven't returned to nuclear propulsion. Secrets that might reveal a different reality altogether. As we stand at the precipice of this new frontier, gazing outward towards distant worlds, let us remember the lessons of NERVA. For in the silence of cancelled programs,